red, orange, yellow, green, blue, or violet, depending on the frequency, or wavelength. The red end of the spectrum consists of longer waves, lower frequency, than the blue or violet end. The wavelength of red light is about 700 nanometers. A nanometer is 1/1000th of a meter, or 10 to the negative 9th power meters, while the wavelength of violet light is only half that. Because light moves so fast, the frequency of oscillation is enormous. Blue light oscillates a quadrillion, 10 to the 15th power times per second. Red light oscillates about half as fast. In physics jargon, the frequency of blue light is 10 to the 15th power hertz. Can the wavelength of light be longer than 700 or shorter than 400 nanometers? Yes, but then it's not called light. The eye is insensitive to such wavelengths. Ultraviolet rays and X-rays are shorter than violet waves, and the shortest of all rays are called gamma rays. On the longer wavelength side, we have infrared rays, microwaves, and radio waves. The entire spectrum, from gamma rays to radio waves, is known as electromagnetic radiation. So, Alice, the answer to your question is that light is definitely composed of waves. But wait, not so fast. Between 1900 and 1905, a very disturbing surprise upset the foundations of physics and left the subject in a state of complete confusion for more than 20 years. Some would say it's still in confusion. Building on the work of Max Planck, Einstein completely subverted the dominant paradigm. We don't have time or space for the history of how he got there, but by 1904, convinced that light was composed of particles that he called quanta. Later they would be known as photons. To shorten a fascinating story to its bare bones, light, when extremely dim, behaves like particles, arriving one at a time as if they were intermittent bullets. Go back to the experiment in which light passes through two slits, eventually arriving at a screen. Imagine dimming the light source to a bare trickle. A wave theorist would expect a very dim, wave-like pattern, just barely visible, or perhaps not visible at all. But visible or not, the expected pattern would be wave-like. That's not what Einstein predicted, and as usual, he was right. Instead of continuous illumination, his theory predicted sudden point flashes of light. The first flash would appear randomly at some unpredictable point on the screen. Another flash would appear randomly somewhere else, then another. If the flashes were photographed and superimposed, a pattern would begin to emerge out of the random flashes, a wave-like pattern. So is light a particle, or is it a wave? The answer depends on the experiment and the question that you ask. If the experiment involves light so dim that the photons trickle through one at a time, light appears to be unpredictable, randomly arriving photons. But if there are enough photons so that they form a pattern, light behaves like waves. The great physicist Niels Bohr described this confusing situation by saying that the wave and particle theories of light are complementary. Einstein argued that photons must have energy. There was certainly evidence of this. Sunlight, photons emitted by the sun, warms the earth. Solar panels convert the sun's photons to electricity. The electricity can be used to run a motor and raise a heavy weight. If the light has energy, so too must the photons that make it up. It's clear that a single photon has only a very small amount of energy. But exactly how much? How many photons does it take to boil a cup of tea or run a 100-watt motor for an hour? The answer depends on the wavelength of the radiation. Longer wavelength photons are less energetic than shorter wavelength ones. Thus, more longer wavelength photons are needed to do a given job. A very famous formula, not as famous as E equals mc squared, but still very famous, gives the energy of a single photon in terms of its frequency. E equals hf. This formula was introduced by Max Planck in 1900. However, it was Einstein who understood that light is made of particle-like quanta, and that the formula applies to the energy of a single photon. The left side of the equation, E, represents the energy of the photon, measured in a unit called the joule. On the right side, F is the frequency. For blue light, the frequency is 10 to the 15th power hertz. That leaves H, the famous Planck's constant that Max Planck introduced in 1900. Planck's constant is a very small number, but it is one of the most important constants of nature, controlling all quantum phenomena. It ranks alongside the speed of light, c, and Newton's gravitational constant, g. H equals 6.62 times 10 to the negative 34th power. Because Planck's constant is so small, the energy of a single photon is minute. To calculate the energy of a photon of blue light, multiply Planck's constant by the frequency 10 to the 15th power hertz, and you get 6.62 times 10 to the negative 19 joules. Energy. And it's not. It would take about 10 to the 39th power photons of blue light to boil your tea. You would need about twice that number of photons of red light. By contrast, with the highest energy gamma rays that have ever been detected, boiling the same cup of tea would take a mere 10 to the 18th power photons. Out of all of these formulas and numbers, I want you to remember only one thing. The shorter the wavelength of a light ray, the higher the energy of an individual photon. High energy means short wavelength. Low energy means long wavelength. Say it over a few times and write it down. Now say it again. High energy means short wavelength. Low energy means long wavelength. Predicting the future? Einstein pompously declared in a letter to Max Bohr on December 12, 1926, "God does not play dice." Niels Bohr's response was sharp. "Einstein," Bohr scolded, "don't tell God what to do." Both physicists were pretty close to being atheists. It would seem unlikely that either of them contemplated a deity sitting on a cloud trying to roll a 7. But both Bohr and Einstein were struggling with something totally new in physics, something that Einstein simply could not accept: the unpredictability that the strange new rules of quantum mechanics implied. Einstein's intellect rebelled at the idea of a random, uncontrollable element in the laws of nature. The idea that the arrival of a photon was truly an unpredictable event went deeply against his grain. Bohr, by contrast, may or may not have liked the idea, but he accepted it. He also understood that future physicists would have to rewire themselves for quantum mechanics, and part of that rewiring would include the unpredictability that Einstein dreaded. It wasn't that Bohr was better at visualizing quantum phenomena, or that he was more comfortable with it. Anyone who is not shocked by quantum theory has not understood it, he once declared. Many years later, Richard Feynman opined, "I think it's safe to say that no one understands quantum mechanics."